MCT4C, Vectors Day 6. We're going to have fun, okay, sort of fun, velocity and displacement, and some of these questions are going to make you think. All right, example number 1. An airplane is flying with an airspeed of 435 kilometers per hour heading due east. That doesn't mean that's where he goes, that's where he's headed the plane. There is a wind 40 kilometers per hour blowing from the south. Find the ground velocity, or what it would look like to us looking up at the plane from the ground. So a picture is worth 1,000 words. So this plane, I'm going to call him P, is heading due east. Vector P. There is a 40 kilometer per hour wind, let's call him W, very creative vectors here, from the south, so heading north. So there's my wind, there's where the plane is headed, and the resultant would be, since I've got it tip to tail, this is the resultant, or where the plane is actually going as we view it from below. We have actually created a right angle triangle because we're going due north and due east, so we can use right angle trig. If I want to find the magnitude of the resultant, I can use Pythagorean theorem. So the magnitude of the resultant squared is the magnitude of the plane squared plus the magnitude of the wind squared. So I have 435 squared plus 40 squared. Notice again that the wind is fairly small, not negligible, but small compared to the velocity of the plane, so it will push it a little bit, but not monumentally. So, according to my calculator, 1,90825, the magnitude of r, once I've taken the square root, is approximately 436.8 kilometers per hour. I would also like to know what direction it's going. That's kind of important to the people on the plane. So I'm going to look for this angle here, which, since it's an angle from due north, would be a bearing precisely. I can use right angle trig to find that angle. Since I know values here and here, it is somewhat possible I made a mistake with my resultant, so I'm going to use the numbers I was given. I am going to use the trig ratio, opposite and adjacent. I'm going to use a tan ratio. So for the direction, I'm going to use tan theta equals opposite over adjacent, 435 over 40. To find that angle, I want the second function tan, the inverse tan of 435/40. I will get an angle of approximately 84.7 degrees. Therefore, the airplane will travel at 436.8 kilometers per hour at a bearing of 84.7 degrees. Example number 2 is one of displacement, very same principles. A boat travels 2 kilometers north 40 degrees east, and then travels 4 kilometers north 15 degrees west. Find the resultant displacement. I'm going to draw my diagram fairly large so that I can see all those angles that we're going to be working with. So we have a boat, and he travels 2 kilometers north 40 degrees east. So I'm going to draw a north arrow just to get myself anchored. Okay. The boat, 2 kilometers north 40 degrees east, so I'm heading north, turn 40 degrees towards the east, and That will be our boat. And then he travels 4 kilometers north, 15 degrees to the west. So I'm just going to draw a very small little north arrow here. It helps my eyes. I hope I'm not confusing you. But then he changes direction and heading north and then 15 degrees towards the west. I've tried to make my vector twice as long as the other one. The angle right in there is 15 degrees. So heading north, turning 15 degrees towards the west. I have my 40 degrees down in that corner. And I have a confusing but somewhat accurate diagram. I would like, first of all, the resultant displacement. So we started down in the bottom corner here, and we end up at the top here. Let's do that in red. Start down here, end up here. Here is my resultant. Now I have made some assumptions by my diagram because it looks like, to me, that my resultant is going to be northwest. I might not have drawn it accurately. So I've got a rough idea of the length and the direction of my resultant vector, but we would never trust our eyes. Let's find the displacement first of all. And since I have a triangle that I cannot assume is a right angled triangle, I am likely going to be using the cos law. I've got a side of 2, a side of 4. I want my resultant and I need the angle between them. And that's where this gets a little bit tricky. Let me just add to my diagram an east-west marker in there. That helps my eyes know what angles I have. I have a Z pattern. I'm going to introduce the color blue. I have a Z pattern from this north to this vector, which would also be the same angle right there. So in my diagram, I have 40 degrees. So my angle here, I'm going to call it theta. It is a straight line. Subtract the 15 degrees right here. Subtract the 40 degrees down here. And what I am left with is theta in between. So my angle is 125 degrees. To find the magnitude of that resultant, I am going to use r squared equals 4 squared plus 2 squared minus 2 times 2 times 4 cos 125. Making my brackets my friends, and I'm making sure I'm in degree mode. I end up with the magnitude of the resultant squared is approximately 29.2. The magnitude itself is approximately 5.4 kilometers. Does that look reasonable according to our diagram? I have a 2, a 4, and a longest side of 5.4. Yes, it looks reasonable. We have difficulty finding the direction. I would like to be able to describe this direction as a bearing. I need, however, to find angles in my triangle. I have that angle theta is 125 degrees, and I would like to find the entire angle in the bottom corner, knowing that 40 degrees of it is already spoken for, and the remaining will be my bearing. I need to use the sine law because I don't have a right angle triangle. I have a sine of 125 degrees. Look across the triangle, 5.4 equals sine. Let's call that bottom angle the whole thing, angle alpha over 4. 4 times sine 125 over 5.4. Alpha is equal to second function sine of this big mess, 4. Sine 125 over 5.4. That gives me an angle of approximately 37.4 degrees. So that tells me a number of things. First of all, my diagram isn't correct. My diagram should have had my resultant, so I would have my 2, my 4, and my resultant would actually be a little bit northeast. This whole angle is 40 degrees down here. And if the angle in my triangle is 37.4, that means my bearing is actually 2.6 degrees. My vector, my resultant, is actually headed a little more towards the east than towards the west. So I drew my resultant incorrectly. Final answer. Therefore, the boat's displacement is 5.4 kilometers north, 2.6 degrees east. Example number 3 is about velocity, the same as our first question, but this one is a bit more challenging. We are going to try to answer this problem in 2 different ways. The first method that we're going to use to solve this problem is using component form from a few days back. We are going to look at the airspeed of this plane and the wind and look at its horizontal and vertical components and put those 2 things together to get our resultant. So let's come up with a diagram first that will allow us to get a sense of this situation. So the plane is heading northwest. If it says northwest, we can assume that it is exactly northwest, which would be 45 degrees from west towards the north. So our airplane is northwest 489. Let's call it P for plane. Okay. We have a tailwind of 62 kilometers per hour from south 25 degrees west. So our wind is headed in the direction from south 25 degrees west. So he comes from this way. Head south, turn 25 degrees to the west. We have this. I'm going to move that vector right here. Has the same vector, has 25 degrees there. It has a speed of 62 kilometers per hour, and he is W. We know from the diagrams that we looked at yesterday that the resultant would be the diagonal of the parallelogram formed by those two vectors. And my resultant will be approximately there. If I have them set up tip to tip, then my resultant will be approximately there, because I know when I add vectors, I'm going to try and mirror this. I have my plane. I'm going to move my wind so that it is tip to tail, and my resultant would be like that. Okay. So my resultant appears to be heading in a somewhat northwest direction, and we would like to come up with a solution for that. We're going to do this a little bit differently. We're going to look at the horizontal component and vertical. First for the wind and then for the plane. If I want to know the magnitude of my wind in the horizontal component direction, I can write it like that. Saying vector W as a horizontal component, I want its size. From the other day when we were looking at component form, I know that I want the cos of the angle because I want, running out of colors here, I want this component right here, which would be, this is 65 degrees, which would be adjacent over hypotenuse. I know that I want to use the magnitude of 62. I know that I want to use cos for a horizontal component and the angle, 65 degrees. That will give me a horizontal component of 26.2. For the airplane, the horizontal component, I can write fancy notation like that. The horizontal component for my plane, so I'm using an x direction, is, again, we're going to use cos. So the magnitude of the plane, cos, the angle between the airplane and the x-axis is 45 degrees. And that will give me 345.8. I know that my plane has a horizontal component of 345.8 left or northwest. I know that my wind has a horizontal component right or northeast. Going to want to keep that in mind. For my vertical components, I have the wind, and the plane, and I'm going to write them with a subscript little y because I want the up and down vertical component in the y direction. My wind is 62, and I know for the vertical component I am going to choose purple. I am looking at the vertical component right here. Nope, it's giving me green. Sorry about that. That would be my vertical component for my wind, and it will be 62 sine 65. I still use that 65 degrees because what I am looking at is actually the vertical component right there. That will give me approximately 56.2. And we know that that word is upwards or north. For the plane, the vertical component, which is right here, is going to be 489 sine again, because I want the opposite and using the hypotenuse. Sine of 45 is approximately 345.8. It is also up or north. I'm going to draw another diagram. I have vertical components. Let's do vertical. Both of them are up. So I have 402 up. I'm going to write it as the magnitude, come on, the magnitude of the resultant in a vertical is going to be, since both of them are up, I have added those two, I will get 402 upwards. The horizontal of my resultant is going to be x. Because I have left and right, they're opposite, then I would subtract them. And the one to the left is much stronger than the one to the right. So we have a horizontal component left of 319.6. To get my resultant, I have basically come up with a horizontal component of 319.6 and a vertical component, draw better than I am, of 402, and my resultant takes the vertical and the horizontal components, puts them together, and gives me my resultant. I have created a right angle triangle. Math on this is really sweet. The resultant squared equals 319.6 squared plus 402 squared using Pythagorean theorem. My resultant is 513.6, and that looks reasonable. The angle is also nice to find. This will be a direction north from west if I use this one. I am going to use tan because I have been given my opposite adjacent. So tan of theta equals opposite over adjacent. Theta is second function tan of 402 over 319.6, whatever that is. On my calculator, theta is 51.5 degrees. Therefore, the ground speed, what it looks like that plane is actually doing, is 513.6. Got to follow the same units, kilometers per hour. At our angle is between west and north, so west 51.5 degrees north. Or put this one in brackets. We're going to go the other way because it's more common. Start with north, turn 39 degrees towards the west. The second method that we're going to use is not using component form. We're going to draw our diagram again and use the coast law instead. So we have our north. Our plane was northwest. Our wind, we need to do tip to tail. And I've drawn my wind much shorter, should be proportionally shorter. And our resultant, we know what's here. We know that there was 45 degrees here between west and north and the blue. We know when our wind was drawn down here, there was 25 degrees. We need to come up with the angle theta in there so that I can use the coast law to find my resultant. I know these numbers. The plane was 489 and the wind was 62. So if I had the angle between them, I would be able to use the coast law. This can be the tricky part, is finding the angle. The angle, if I draw a little north, south, east, west up here, is made up of 65 degrees here, because I know that is 25, and 45 degrees here, because that is directly northwest. So there are 45 angles all over the place. That means my theta is 65 degrees plus 45 degrees, which is 110 degrees. I want to find the resultant. I am going to use the coast law. Resultant squared equals 62 squared plus 489 squared, take away 2, 62, 489, cos 110. In degree mode with the brackets, we end up with the resultant. Approximately, oh my, 513.5. So notice this took us a lot less time and writing to come up with our resultant, but determining that angle can be a little tricky on the eyes and the diagrams. So be very careful here, and the math is super. If we want to come up with the direction, I would like to know an angle here so that I can give a direction from west, north from west. I'm going to use the sine law again. Sine 110 degrees over the resultant, which is 513.5, is equal to sine of theta over its opposite side, which is w, which is 62. Multiplying both sides by 62. Makes 62 times sine of 110 degrees over 513.5. Sine theta is approximately 0.1135. Theta is the second function sign of that answer. Theta is 6.5 degrees. That means that my direction is head west, turn 45 plus 6.5 degrees towards north. .5 degrees. Same angle, same magnitude. Please try. Page 58, 59. Number 1, 3 to 8, 11 to 14.